I had a few people ask me to explain Endianness because while they'd heard of Endianness and knew that some processes are little-endian and others are big-endian, they just couldn't quite get their heads around what that means and how to deal with it. So in this video, I'm going to explain what Endianness is and why you probably don't need to worry about it, and also a few other juicy tidbits here and there. Unlike others, I'm not going to explain it in terms of an egg because this isn't Lilliput and Gulliver hasn't traveled here. Let's get started. So what is Endianness? It's all about how large numbers are stored in memory. So let's first have a look at the way we write numbers as humans. So take number 12,345. We start with the largest digit, the 10,000, and we write it from left to right. So 1, 2, 3, 4, 5. This is, without you knowing it, a big-endian format because we start with the largest, the biggest or most significant digit first, and then write it down to the smallest. However, theoretically, we could also write it the other way around, starting with the least significant digits, so the 5, and then writing it in increasing order, so 5, 4, 3, 2, 1. Confusing? That's only because you're so used to writing numbers in big-endian format that anything else looks weird. If everybody decided or agreed to write numbers in little-endian format, then that would be the norm, and it would be big-endian that you would find confusing or weird. Now, in the computing world, we do have CPUs that are big-endian and CPUs that are little-endian. Heck, we even have CPUs that are considered bi-endian, so they can do both. Why? Why on earth do we have to put up with this in the first place? Well, back in the 60s and 70s, so ancient times as far as computing is concerned, there were very few standards, so things weren't standardized, and you had multiple companies vying with each other for global dominance. They were competing against each other. And as any good entrepreneur knows, you need to differentiate yourself from the competition. So if one company did things one way, then other companies would do things the other way in order to differentiate themselves from each other. And then they would explain why their approach was better than their competitors, whether it's true or not. So Intel went little-endian with their x86 CPUs, which ended up in PCs, while companies like Motorola went for big-endian, which they used in their 68,000 series, which ended up in the original Macintosh computers and Commodore Amiga. Let's take a closer look at how this is done in computers. So with computers, numbers are stored in a binary format. So ones and zeros organized with the basic unit being 1 byte. So 1 byte is 8 bits. And with 1 byte, you can store any number between 0 and 255, or if you're doing signed numbers, minus 128 and 127. You can also represent all the letters of the alphabet more using ASCII coding with 1 byte per character. And everything is fine so long as you stay within those narrow ranges. But of course, we have much larger numbers. So what happens when you need to represent large numbers? Obviously, you're going to have to use multiple bytes to store it. So if you add an extra byte, you get 2 bytes, 16-bit number. You can represent any number from 0 to 65,535. Double it again to 4 bytes, so 32 bits. And you can go up to just over 4 billion. And if you double it again to 8 bytes or 64-bit, which is what modern computers tend to use, then you can store insanely large numbers. And here's where Endianness comes into play. In what order do we store those bytes in memory? Let's take the number 324,508,639. So this in hexadecimal format is 13579BDF. And we're using hexadecimal because 2 hexadecimal digits fits cleanly into a byte. So we can separate this out into 4 bytes already. In the big-endian system, we start with the most significant byte, so the large end of the number, and we store that first in memory, and then next come the lesser significant digits. So 13, 57, 9B, DF. That is our number stored in big-endian format. With little-endian systems, we swap things around, the other way around. So we start with the least significant byte, which comes first, and then we go in ascending order. So we end up with DF, 9B, 57, 13. And both of them represent the same number, just using a different endianness. And that, in an eggshell, is endianness. It's simply the order that the bytes of large numbers get stored in memory. By the way, the name endianness does come from, or was inspired by Jonathan Swift's classic novel Gulliver's Travels, in which Lilliput and Blefuscu were two kingdoms that had a war over whether eggs should be eaten from the little end or the big end. So little enders, big enders, little-endian, big-endian, you get it? Anyway, be grateful that the big companies only competed on the byte order, because they could also have gone big-endian and little-endian on the order of the bits within a byte, in which case there would be 4 possible different combinations and it would make our brains seriously hurt. While this is all very interesting, as a programmer, you're unlikely to have to worry about it most of the time. So the CPU reads and writes numbers in whatever its native endian format is, and it does this automatically. So long as your code doesn't need to interact with data from a system using different endianness, then everything is in the same endian format and it all just works. You only need to worry about endianness in specific circumstances. So the first one being transferring data between computer hardware of different endianness. And that can include transferring data between the CPU and a peripheral. For example, my Amiga OS graphics drivers have to interface a big-endian PowerPC CPU with a little-endian GPU. So the data needs to be converted of endianness, but when transferring it in either direction. Second situation is transferring data between computers, even if they're both little-endian, because the TCP/IP network protocol has decided to go with big-endian for addressing. And finally, loading and saving of data to disk, to or from disk, when the data format is in a different endianness of the CPU. Oh, and there's one more. When you're looking at memory in a debugger on a little-endian system, and that's because you look at the memory as a big array, and the numbers in the memory will be stored in little-endian format, so you have to mentally do the swapping. This is one case situation where the computer can't do the endianness swapping for you automatically, because in order to do the endianness swapping correctly, you need to know how big the number is. So let's take our number again, the number we used before, the little-endian number DF9B5713. If you want to convert that to big-endian correctly, we need to know that it's a 4-byte number. So if you swap it as a 32-bit 4-byte number, then it becomes 13579B-DF, which is correct. Now, if you treat it as two 16-bit numbers, then you get a totally different number. If you still find endianness confusing, then I have some great news for you. Endianness is likely to become less and less important because little-endian format CPUs are now dominant, like so dominant that Linux for PowerPC has switching to little-endian. So PowerPC is one of the CPUs that can handle both big and little-endian, but maintaining drivers for big-endian CPUs in an increasingly little-endian computing world was just getting too heavy, and I know all about that because I have to deal with it when writing Amiga OS graphics drivers. So the easiest solution was to switch the endianness that the CPU uses by default to match the attached hardware. So now you understand endianness, but how do you convert between little and big endian or vice versa when you actually need to do it? That's a topic for my next video, which should appear over here. That's it for now. We'll see you next time.